mirror symmetry So mirror symmetry is actually a phenomenon which we largely, which we don't understand from a general point of view, but for which we have some really astonishing examples. One of them is the examples, the first example that occurred, which is a quintic hypersurface of Calabi-Yau type. So let me define the hypersurface given by, this Fermat equation inside P4, which is Calabi-Yau. We have said this in this way in the last few lectures. And let me study the cohomology of this. So from a very, let's first study the cohomology with its double grading. Okay, and I would like to keep track of the rank of the spaces, the dimension of those vector spaces. And I write, as usual, the Hodge diamond. And, 0, 1, 3. So this Hodge diamond in this specific case is given by the following numbers. Okay, so notice that you can read on this diagram the odd cohomology, which is concentrated in degree 3 and has dimension 204. And there are no other odd cohomology contribution for this variety. And the entire even cohomology is of dimension 4. And it all consists of classes of B degree of type P. So mirror symmetry is going to be about finding another Calabi-Yau variety, which is dual to that one, whose Hodge diamond is going to look like this. At a very, very superficial level, we can phrase this duality in this cohomological way. So what I'm looking for is a variety which I note in this way, X dual, and which has this as a Hodge diamond, which is a very simple odd cohomology and a huge even cohomology. So now, how is that constructed? Well, this has been constructed first in a very simple way. We mod out X by an abelian group spanned by 3 matrices acting on the coordinates as follows. E 2 pi I over 5, 1, 1, 1, E minus 2 pi I over 5, and so on. Let's see. G2 is going to be the diagonal matrix with entry 1, E 2 pi I over 5, 1, 1, E minus 2 pi I over 5. And G3, 1, 1, E 2 pi I over 5, 1, E minus 2 pi I over 5. And, well, you may wonder why I have chosen these 3 matrices and not other natural choices, but you know. Now, one thing you should notice first is that this matrix, these matrices have determinant 1. And one thing you may be worried about is in what sense I should understand this quotient. So usually, if you mod out a smooth variety by a finite group, then you get a singular variety. But since the talk of Dimitri, you should not worry about those kind of things. Because you know that those quotients can be intended, can be understood in the language of orbifolds. And in fact, we have treated things that look much more difficult than those, which are things that look locally like these finite quotients, and then are patched together along those subcharts that Dimitri has defined. Now, this is a much easier thing to define. Nevertheless, it has this is a delicate step, and we maybe should take care of it by recalling that cohomology for orbifolds is slightly different. It has been defined by Chen-Ruan, and it's called orbifold Chen-Ruan cohomology. And I think it's probably better not to say, as usual, that YPD is going to define it. But let's see. Let's try. So let's see. This is an easy case. And I think I flipped through the notes of YPD, and there is no case of non-abelian quotient. So let's define this cohomology for abelian quotients. OK, so if I get X mod G, where G is an abelian group, what is this cohomology? Well, as a vector space, you can understand it as follows. Well, consider X, and for every element of G, you can consider the G fixed locus inside X. OK? Then you compute its cohomology. G naturally acts on this cohomology, naturally and also quite nicely, because G is abelian. Anyway, then you have exactly the cohomology, the orbifold cohomology. Now, there is a slight delicate point, which is about the degree. Actually, let me do it for PQ. OK? So if you know what is PQ for an ordinary cohomology, let me slightly modify this here in order to get PQ for orbifold cohomology. Minus something which is called the age of G. This is defined in many courses. Even in Gabriel Farkas' course, you will find this invariant defined. What is the age of G? Well, take G and suppose, take a point in xg, the fixed locus by G. Well, that point has a tangent space inside X. And G acts on this. And now write down the matrix giving you this action. Well, you will get a matrix of the same dimension of X, written like this. You can diagonalize it, and for a suitable basis, you can get this. Now, notice that those things are all roots of unity. So you can choose lambda to lie inside 0, 1, and define the age of G as the sum of lambda I. OK, once you have done this, then what you get as a cohomology is precisely the Hodge diamond that I spoke about. So, yeah.
What does it represent?
This matrix represents the way G acts on this tangent space. There are going to be, if G fixes something, there's going to be some 1 in here. Okay.
Why age of G is an integer number?
No, it's not. A priori, it isn't. In this special case that we have studied, it is. It's precisely because these G's are all of determinant 1. But in general, you can think of actions which not this property, and then you may actually get something which has rational grading. And you have to live with that, and it's even fun to live with that. Okay, so let's get to a somewhat deeper, less elementary picture of mirror symmetry. And so now I'm going to try and provide a deeper picture of this symmetry. So I start again from this variety, but we're going to give a deeper look into the mirror. So here is still my variety, but I'm not going to do ordinary cohomology, but rather quantum cohomology of X, which is another way to say Gromov-Witten theory in genus 0. And this what is going to be gradually defined in the course of YPD. Actually, let's start from the mirror. Let's start from the dual variety. So what does it actually mean that this dual variety has H21 equal to 1? We're going to focus on this because this duality is actually saying that the H21 of this variety is the same thing as the H11 of the variety over there. Okay, so what does it actually mean? It means that this H21 is about the deformations of this variety, or this orbifold, if you want. And it means that there is a one-dimensional universal deformation of X dual. So let's try and give a picture of it. So to define it, I have to perturb slightly the equation of X by adding a parameter So as you notice, I have deformed X. But I've taken care of deforming X in such a way that this action is preserved. Because since the action preserves the has determinant 1, all those variables are, or this product is going to be fixed. Let me call this by f psi. And let me say that this can be used to define again, an orbifold. But this time for every psi. So every time I fix a psi to a certain value, I'm going to get an orbifold. Well, some orbifolds are going to be very singular. The first one is the one for psi equals 0, which is X dual, the one I started from. And then I move all the way to psi equal infinity, and there I get an orbifold which has a very, very nasty singularity. In fact, what I'm interested in is more the behavior of this family at the neighborhood of infinity, where I can still look at the cohomology. If I forget to say it's the Chen-Ruan cohomology of the orbifold. So, with complex values. And notice that at every point in the neighborhood of infinity, I can define this four-dimensional space if I just restrict to the odd-dimensional cohomology. So let me do this. Let me just restrict to the odd-dimensional cohomology. Okay? So this is a four-dimensional vector space on a point, and it forms a four-dimensional vector bundle on the neighborhood at infinity. And this four-dimensional vector bundle contains a distinguished lattice. Okay? And this lattice varies in a non-trivial way. If you go around the point at infinity and you come back, this lattice is going to be transformed by a monodromy operator which is a linear operator which is non-trivial. What I'm saying here is that I'm having a vector bundle plus a flat connection, which already appeared in the talks of Pandaripande as the Gauss-Manin connection. So the idea is to actually not to mimic, but to find from a completely different point of view the same structure. A vector bundle on a puncture disk equipped with a non-trivial flat connection. This flat connection is highly non-trivial, and that's what we're going to do here. So this stuff that I'm hiding now is what is usually called the B side of mirror symmetry. Now we are getting back to the A side of mirror symmetry. And, well, the course, here is where I'm going to leave many things to be defined, to YP, and also to Alessio Corti. Alessio is going to speak probably more precisely about the Dubrovin connection. It turns out that what we can do here is to set up a puncture disk. And we're going to consider a vector bundle whose fiber are the even cohomology of X. If you want, you can write Chen-Rohan, although this is probably redundant because there is no funny cohomology here. Okay, so this is just the ordinary cohomology, which is generalized in Chen-Rohan framework. And now Gromov-Witten theory in genus 0, or quantum cohomology, yields something like a connection, a flat connection, Dubrovin connection. I don't know, I noticed that this occurs in the notes of YP. I don't know if this is going to be developed. I know that Alessio is going to say something about this operator nabla describing the way the quantum product varies. Essentially, you should see this structure as defining a ring structure. So far, we have just spoken about vector spaces. And this ring structure, this product that you are defining on the space, varies along those fibers. And in this sense, it naturally yields a flat connection. What I'm more interested in is to address the following question. Apart from this side, I think you can notice that the two blackbirds have a striking difference. The lower one has more structure, has more, presents a more complete picture. We are not considering only what happens around infinity. We're also having a family of orbifolds for which we can repeat the same story and study the monodromy of the connection around the point at 0, for example. So what I mean by filling in this picture, this framework of mirror symmetry, is to look at what is the mirror of what happens here. Okay, so the question we are going to focus on is how to fill in this side of the correspondence. Gromov-Witten theory tells us what is matching this side. In fact, this is the theorem of Gieventhal and Liu Yao, who computed Gromov-Witten theory in genus 0 and then established an isomorphism between this 4-dimensional vector bundle with flat connection and this one, a mirror map exchanging the two bases and respecting the two structures. And what Yongbin and I did was finding a theory here which does the same thing and matches the local structures around 0. Okay, so what is that theory? This is a really surprising thing. This theory is the theory of level structure, which has been discussed in some course of Gavril Farkas. So to complete this blackboard, I should put here the enumerative geometry instead of Gromov-Witten theory, which gives I should put here a theory which we're going to define, which is the enumerative geometry of curves with line bundles whose Lth power is going to be isomorphic to some canonically defined bundle. So usually we consider the canonical bundle, but also any other line bundle would be interesting. For example, you can also have versions of this with a trivial bundle, with other products of this. And these things have a geometry which is interesting in its own right. And so I will develop the theory of these things called the level curves or spin curves in the rest of this lecture via some examples. This is going to be very similar to what Dimitri has done for elliptic curves when he described the moduli space M11 of Riemann surfaces of genus 1 and showed how to compactify it. So I'm following his scheme, and I'm trying to approach this compactification via examples. Okay, so after this introduction, let me just set a moduli problem. So here I have an orbifold. And to keep things simple, I'm going to just consider the orbifold of curves with points and with a line bundle, such that the square, the second power, is isomorphic, again, to keep things simple, to the trivial line bundle. And I'm going to assume first that this is a smooth curve. Okay, this is going to be examples of level curves. Okay, so this is an orbifold which covers MGN, which has been discussed in the previous lectures, and is the stack or the Riemann per stack or orbifold of smooth curves with M marking and genus G. And now, as you know, this is not compact, but you can compactify. And the way you compactify is very simple. Like Davis said, you just draw a line here. But it's almost as simple as this. This was a joke, but in fact, if you just draw a line here and replace this by stable, then you really won. Okay? So stability is a notion that is not very hard to introduce. It's just the least singular curve that you can think of, plus a certain nice stability condition. And now you may actually think whether here it's enough to allow stable curves into this picture. Okay, so this is a naive guess. Oh. And I don't know if this is going to be very well recorded. So allow stable curves is a bad idea. And that's what we're going to discover with genus 1 and 1 marking. So let me do this in this case. smooth curves of genus 1 with one marking, which is elliptic curves. And now we're going to try and compactify this following this naive idea. Now, I'm sorry I have to erase this football, but it's going to be just in order to write another football who has special points like this and have been introduced by Dimitri at some point. Let me see. So the portrait that Dimitri has given was one of a one-dimensional orbifold, for which every point represented an elliptic curve, apart from the one at infinity, which represented a singular curve. Okay, so this point, for example, represents the elliptic curve given by C mod a lattice. Now you may wonder, where is the marking? Well, the marking is the lattice, the class of the lattice. Okay, so and now you are actually trying to solve this problem over this curve, which is finding line bundles whose square root, whose second power is trivial. Now notice that the Picard group of E, well, is the group formed by line bundles, right? And the operation there is tensor product. But this curve has also an operation, which is the sum. And as you know, there is an isomorphism here. So this makes it very easy to find who are the points whose that sum to themselves give 0 inside this group. There are actually 4 solutions, and we can name them all. So one is the lattice itself. Let's call it 0, say, or if you want 0 plus the lattice, but I will forget about that. And then 1/2. Well, let's write the lattice as follows: z plus tau z, which is a renormalized lattice if you follow Dimitri's talk. Okay, so these are the only 4 points whose second power, if you want to, such that multiplied by 2 you get the trivial element, the only 2 torsion points of the elliptic curve. Okay, so if you consider any tau, then you get an automorphism group acting on E, which is isomorphic to Z2. And that actually fixes, if you carry out the computation, fixes each one of these 4 points. So if it acts on these 4 points by fixing them. It doesn't act trivially on the curve, but it fixes these 4 points. So let's move to a more interesting point, which looks like those points where the pentagons were meeting. And this is this elliptic curve. Here, the automorphism group is special, and as discussed by Dimitri, is isomorphic to Z4. And now, if you see how this acts on these 4 points, well, you have only 3 orbits. So that's. And now, there is another, and only one, special point, whose automorphism group is Z6, and the number of orbits is 2. Okay, let's now switch to something more interesting, which is the study of the singular curve. There is only one singular curve at the boundary, and it looks like this. You take P1, and you glue to each other 0 and infinity, and you mark it at P1 equal 1. So what is a line bundle on this curve such that the second power is trivial? Well, of course, if you pull back this line bundle on P1, then you must get a trivial line bundle. Okay, so one fact is that this should be trivial, should be of degree 0, so there is only one choice. And then this line bundle is going to be determined by the way you glue LP1 restricted to 0 and LP1 restricted to infinity. So here, this amounts to specify a non-zero complex number. And there are only two possible choices of non-zero complex number whose square is equal to 1. Lambda equal 1 and lambda equal minus 1. So as you see, here is the first time you realize that something is failing to be constant on the boundary. And if you look at the way the automorphism group operates on this fiber, well, here the automorphism group is going to be Z2, and the orbits are going to be just 2 points. Okay, so now you carried out a study of this moduli space, which is careful enough for you to be able to count that this moduli space cannot be compact. And in fact, it's an easy computation. The point I'm trying to make is that every time you say something at the level of orbifold, there is a concrete picture that follows you, which is the picture at the level of singular coarse spaces. Okay? So all the objects we have named over there have a concrete corresponding picture. And this one, as we know, is a projective line. Okay? So the one we have described over here must be a four-sheeted cover, connected or not, I don't know, of P1. And you can even try and compute what is, like in the course of Motohiko Murase, what is the degree of this cover? Well, what is the degree of the canonical bundle of the cover? So let's suppose that the cover is compact. So if it is, the degree should be 4 times the degree of omega P1 plus the sum over the ramification, the points where this forgetful morphism F is ramified, and this formula. So what this formula says is that we have to compute for every fiber, every special fiber, 4 minus the number of orbits. Okay? So what does 4 minus the number of orbits give in those cases? Well, in this case, it gives 4 minus 3, which is 1. In this case, 4 minus 2, which is 2. And in this case, 2. So if you put everything together, then you get minus 8 plus 5, which is minus 3, which is obviously a contradiction. This cannot be a smooth cover. Well, it could be singular, you may say, but in fact, it's very easy to see that this is a smooth four-sheeted cover. This poses very little problem. Okay, so now we have to find why and where are those points hiding. And we have to define a new compactification. And we have to abandon this idea that the compactification is going to be as easy as replacing smooth curves by stable curves. So this is what I'm going to do here. I'm going to introduce curves which are more general than the stable curves. You've seen stable curves for a week, so maybe you are ready now to explore some curves which are not stable curve in your ordinary sense. Today we're going to do it in this way. We're going to add, let me say it here. We're going to consider the space of, so these are curves with only nodes, just as stable curves are. Okay? So when I say nodes, I say something that locally looks like this. Okay? But now I'm adding a new information, which is that I'm requiring that all those nodes are orbifold nodes. Okay? So locally, they don't look like this, but they look like the quotient of this local picture of a node by Z2. And now I'm considering this chart around the node. Okay? Then I'm still requiring that the number of automorphism is finite. Or the group of automorphism is finite. Okay? So, and I'm still marking points which are smooth and distinct. Well, in this case, there is only one marking. So, okay, so what have I changed with respect to M11 bar? Well, I've only added one special curve, which is the boundary curve, which I should replace here. So all this thing goes away. Okay, so what it looks like? What does it look like? Well, it's a curve which I'm going to write like I usually write stacks with curly letters. And it looks like the E that I have used earlier, which used to be P1 with 2 points attached, but modded out by a Z2 action. The Z2 action is a very easy one. It's sending Z to minus Z. So notice that this action fixes 0 and fixes infinity. So it fixes this node that I have created by gluing 0 to infinity. And it doesn't fix any other point. Okay? So I have defined in this way one curve that locally looks like I said, because if you take a local picture around this node that I have created, the picture looks like this, with X and Y sent to this. And now the question is, what are line bundles on these curves, and what are line bundles on E such that the second tensor power is going to be trivial, just as we did for the other curves. Now, one easy way to understand those things is to pull everything on LE, on E. Okay? So E maps on this orbifold or on this stacky curve. And you can pull back L on E. And now, LE is going to satisfy again the condition that the second tensor power is going to be trivial. Okay? But it should also be equipped with a Z2 action, just as E is. Okay? So this time, if I continue my picture as I did here, I should, let me just squeeze the picture into here. I used to have oops, sorry. I used to have 2 points, right? And now these 2 points are twice as many. Because to every point, which used to be a square root of the trivial line bundle on E, I should add a copy which comes from changing the involution along the fiber. Okay? So I have 2 possible ways of acting by Z2 on a line, and these 2 possible ways yield twice as many roots. So this time I'm in a situation in which every time I count, I get the same number of points, and then I would like to finish the analog computation. And that's where everyone learns something, because what is the automorphism group of this stacky curve? Okay, so this is a stacky curve or Orbi curve, and has more automorphism, has more line bundles than the usual one, has more automorphism than the usual one. It turns out that the underlying curve has, as we said, a cyclic group of order 2 as automorphism. Here, we find 2 extra automorphisms, which come from acting on the node in a funny way. Let's write it in this. There exists an automorphism of E that fixes the coarse quotient. Now I can take the coarse quotient and I get a nodal curve with 2 automorphisms. But now I discover that there exists an automorphism that this quotient does not see. Okay? This automorphism is mapping xy in that picture to minus x, y. You may find this very funny because I'm sort of privileging one branch with respect to the other. Okay? But on the other hand, the automorphisms of stacks are defined up to transformations like those. So I could actually say mapping xy to x minus y. Okay, so this is an automorphism that Alessio Corti, who is landing tonight in Lyon, I think, started calling the ghost. And this seems to be a nice name for it. Because when you pass to the real picture, you don't see it. It doesn't move anything. But when you lift everything in the stacky world, which is what this blackboard is devoted to, then it moves something. Let's get back to the real world, which is the one here. Oh, I see. So there are 4 line bundles, and there is this large automorphism group. And it must do something to those 4 line bundles. So if I had if I had a stair, I would go there and tell you what it does. Let's see. This automorphism group is a funny group, as you saw, and it acts non-trivially. It identifies two of those things. Let me see which ones. Okay, so it's hard to... Anyway, it should look like this. It acts non-trivially on those... Sorry, bye. It acts non-trivially. You remember there were two line bundles, one with lambda equal 1 and one with lambda equal minus 1, okay? And the one with lambda minus 1 has a copy which is differently linearized on the fiber. And that copy is identified to the one with non-trivial gluing. This is something that is precisely stated in the most general situation in those notes. You find at some page 13, something like that. Or let me see. A study, precise study of how, at page 21, there is some precise study of how those ghosts act on these level structures. And now we can really forget the orbifold world and see if we actually get something else than a contradiction here. Because this time I'm claiming that we get a smooth and proper four-sheeted cover just by considering R11Z2 or R12, say, the cover of N11Z2 formed by these Z2 stable curves with a marking and a line bundle. And the non-elegant version of this, which is with Roman letters, is going to be a curve which is a proper, smooth, four-sheeted cover of P1. Here, we counted that 4 minus the number of orbits gave 1. Here, we counted the 2. And there, we count 1 again. So in the end, we only have to add 4 and get minus 4. And we finally find that this R211 bar is isomorphic to the disjoint union of two copies of P1. One is just identified to the base, and the other one is a three-folded ramified cover of P1 with some ramifications that appear in that picture. And now, obviously, we can carry out, or I claim that there is a theorem that says that you can carry out this in full generality by simply adding the suitable stacky structure here over all markings and over all genera. Okay? So now you get a nice orbifold cover. You may even try and compute the Euler characteristics of these orbifolds. When you do it for orbifolds, you should not expect an integer. And so, yes, I would recommend this as an exercise to take the orbifold corresponding to this and computing the Euler characteristic as an orbifold. Or even finding that actually the Euler characteristic of this as an orbifold is just a multiple of the Euler characteristic of M11 as an orbifold, which reveals that, in fact, this cover is non-ramified if you look at it from the point of view of orbifolds. So this is a theorem which we're going to see tomorrow. this is an étal and proper morphism of smooth Deligne-Mumford stacks, or if you prefer, of orbifolds. And so what we should do now is to pause a little and realize that there is a lot of work to do to describe the boundary locus of those things, and the analog intersection theory that has been described by Dimitri for moduli of curves. In particular, there is a very useful tool for the enumerative geometry, which is Grothendieck-Riemann-Roch, which is going to be a theorem that I'm going to state tomorrow, which is proven for those kind of curves with this level structure. And then we're going to fit this enumerative theory precisely in the global mirror symmetry picture that I have stated at the beginning. And we're going to show in this third lecture that this is actually filling this gap in the mirror symmetry framework. And then in the fourth lecture, what Youngwin is going to do is to tell you how those people invented the group G that was modding out X and producing the dual, the mirror partner to X, what we denoted X dual. Okay, so you can start thinking about it. You have the definition of orbifold cohomology. You can try to start from a different group. Say, for example, the order 5 cyclic group generated by what I call G1, and try to find if you can find the mirror partner to that group, modding out X in some other different way. In fact, there is a notion of duality between groups that Youngwin is going to describe, and it is due to the physicists Berlund and Hübsch. And as you can see, this kind of things apply in general. You can also have fun with simple elliptic curves or K3 surfaces. Also, those examples are kind of interesting. So this is the program of the fourth lecture on Friday. Thank you very much.
I just want to mention, this has another lane as a modular space or stable map to TED.
Yes. Yeah. This theorem appears in so many places. So Gavril has written this. Okay? And this is just the same thing. Any
Other questions? Otherwise, thanks again for